I've departed from the examples in the text. I just want to work out a few specific items so that you sort of see how these specific cases are handled here. So what do we have here? So we're going to let, what's our rule? Well, let's see. This is not being raised to a power, but this is a function being acted upon by another function. A function being acted upon by another function. We have 12x being acted upon by secant squared. Very often, this is not set in concrete, but very often, if you have a trigonometric function of a quantity, very often you let u equal the quantity in parenthesis here. So if we let u equal 12x, now what's unaccounted for? Well, we have 12x, what's unaccounted for is 3dx. So what's du? Du is, what's the derivative of 12x? Well, that's just 12. So what do we have? This is accounted for with the u statement, the let statement. So we can translate this as secant squared of u. Right? Now, what we have unaccounted for is 3dx. We want 3dx, but we only have 12dx. So what do you need to multiply this by to get rid of the 12 and create it into a 3? I think the multiplier needs to be 1/4. And so if we multiply both sides of this equation by 1/4, 1/4 of 12 is 3dx. Everything is now accounted for. So how do you say secant squared of 12x? You say that as secant squared of u. How do you say 3dx? 3dx is 1/4 du. And so the substitution is exact. And what we're left with is 1/4 du. Secant squared of stuff becomes secant squared of u. And that's a basic form. What is the antiderivative of secant squared? The antiderivative of secant squared is tangent. So we have 1/4 tangent of u plus constant, and we need to translate the u back into the original language. So that's 1/4 tangent of what was u? 12x plus constant. All right, so we'll work through a few more examples of that variety.